The universe, surprise, is full of things that resist being seen, at least through a simple telescope. The cosmos not only emits visible light, it also emits infrared, ultraviolet, microwave, gamma rays. We receive electromagnetic radiation from all corners of the universe, and if you know how to sense it, you can see what's hiding within. But as if this weren't enough, there are still plenty of things out there that we still can't quite observe. So how do we know they exist in the first place? Well, because as invisible as they seem to be, gravity gives them away. You only need to see how the gas and stars from the outermost parts of the galaxy rotate around the centre of the galaxy. Newton's gravitational law tells us that their rotational velocity should diminish the further away from the galactic nucleus they are. But that isn't what we see. The speed of rotation does not appear to change. Some scientists thought that perhaps the way we understood gravity was flawed and that we had to adjust it. Others thought that perhaps the galaxies aren't quite as small as they appear to be, but rather are surrounded by an immense halo that is 9 times more massive than they are, an invisible prolongation whose enormous mass would change the manner in which objects rotate in the galaxy. This idea gathered momentum in light of further evidence. Unexplained galactic movements, gravitational lenses without visible matter, they have even found their footprint in the cosmic microwave background. And this all points towards the existence of something that fills the universe, that exerts gravitational influence on its surroundings, but that we aren't able to see. And this something is called dark matter. And beware, it's important not to confuse dark matter with either dark energy or with antimatter. These are 3 completely different things. Okay, so the next question is, what is dark matter? Let's see what we know about it. We know that it is electrically neutral and dark, that is, it doesn't interact with electromagnetic waves as it neither absorbs nor emits them. We know that it is stable, that is, it doesn't decay over time, and that it is cold, as it doesn't move at speeds close to that of light. So who are the suspects then? Let's ask the Standard Model, the theory which presents us with a list of the most elementary particles of the universe. A pity that they can't help us, neither ordinary matter nor neutrinos. The main candidates fit the profile. This is a sign that in order to understand dark matter, we need some kind of new physics, a physics that goes beyond the Standard Model. This is where exotic new candidates enter the scene, such as axions, supersymmetric particles, extra-dimensional overlords. There are quite a few aspirants to dark matter. Without a doubt, the real challenge is to detect it experimentally, which is quite a hard task given that not only does dark matter not irradiate anything, it also barely interacts with matter. Remember that our planet is within that huge halo. We're constantly being traversed by particles of dark matter, and our machines don't seem to notice them. In spite of that, physicists have a couple of methods for detecting them. On the one hand, there are what are known as direct detection methods. These attempt to observe collisions between dark matter particles and atoms from a detector. For instance, in the case of a crystal, this collision would produce vibrations in a detector's lattice, so that its ionization and small light emission could be measured. These experiments are not easy to carry out, as they need to be shielded and isolated underground in order to dismiss any potential collisions from other particles. On the other hand, there are also indirect detection methods. These find the products of possible interactions with dark matter particles in the halo of our galaxy, neutrinos, antimatter, even photons, which we can capture with a variety of experiments. From gigantic neutrino telescopes at the bottom of the Mediterranean and the Antarctic ice, to detectors mounted on satellites as well as gamma-ray telescopes on the Earth's surface. It's pretty clear that the entire planet is on the hunt for dark matter, and so are we. Multidark is a project led by Spanish investigators, and its objective is to identify and detect dark matter, supporting theoretical investigation as well as experiments being carried out around the globe. So thanks for your work, Multidark, and I hope that soon dark matter will join that part of the universe that we can't see, but can understand. Don't forget to subscribe if you don't want to miss the next video. Thanks for watching, we'll see you soon.